Hi, John here. I just want to do a short video today about cyclonic separation. So I'm on the website now. I'm going to go down. I'm going to click on the Cyclone separator. Load up the cross section. Okay, so the model's loaded up. And what we'll do, we'll have a quick look. This is a cross section of a hydrocyclone. So what have we got here? Well, we've got a hole coming in with a red arrow. I'll zoom in here, and then we're inside the casing here. We can see there's a little bit here sticking out inside the casing. I'll just back through that. And if we're on the cross section side here, we can see this little tube sticking into the cyclone, the main body, and then that hole that we just went through comes out here and impacts tangentially on the inner circle, or the inner diameter, the inner surface of the cyclone. And what else is happening? So there are actually three main holes coming into the cyclone. That one here that we just went through, one coming out here, and one at the bottom. So what are we actually using the cyclone for? What is it? What does it do? Well, there are two different types of cyclone. It's a hydrocyclone, and that's used for separating fluids of different densities. The other type of cyclone is a gas cyclone, and the gas cyclone is more to remove entrained particles in the gas stream. So let's just talk about how the whole thing functions. Now what we'll have, I'm just going to take a gas, we'll just imagine this is a gas cyclone for a moment. We're going to have gas flowing in here. The gas, we'll call it just methane or something. Imagine that the gas from a national pipeline is flowing in here. Now what will happen is the gas from a national gas pipeline actually has entrained bits of water and dirt, sometimes rust from the pipeline, etc. will be carried over into the gas stream. The rust and the gas will enter the cyclone. In fact, we'll go in here, shall we? Okay, so we're going into the cyclone. Here we are, a bit of gas going in. Now what's going to happen? Well, the gas, we're going straight here. The gas is just going to bend around the inside of the cyclone like this. However, the water, if there's any entrained water or dust or rust or anything else, entrained particles, they're not going to be able to change direction as quickly as the gas does. So what will happen is the heavy particles will hit immediately the surface here, and once they've hit the surface, they will drop down and out through the reject hole, which is here in the bottom. Now we call these two holes, in fact this one here, this is a discharge, we'll call that one the reject area, the reject discharge, and this one at the top is called the accept discharge. So we're going to have entrained particles dropping down out of the cyclone, and maybe some moisture or water, and the gas itself is going to travel down. Now this is where it gets interesting. Once it reaches the bottom, due to the vortex effect, the gas is flowing inside the cyclone very, very fast, and this creates a vortex in the middle. So the clean gas, now without any entrained particles, or with less entrained particles of water, etc., will go back up and will exit through the acceptance port here. And if we go down in the reject port or reject discharge, we will have bits of moisture or potentially bits of rust, etc. And that's how it would work for a gas stream. Now for a hydrocyclone, the effect is very similar. We're not going to have big chunks of rust that's just going to hit the sides and drop down. What we'll have is a solution which consists of multiple liquids or multiple concentrations. What we want to do is separate these out. So what will happen is the solution will come in through the port again here. It will spin around inside the hydrocyclone, and what you'll find is the solution that's heaviest will be thrown out to the outside. So that's this inner surface here, and the lighter solution will remain closer to the middle. Now this is essentially centrifugal force. Now centrifugal force means that if you spin an object around, the heavier object will eventually go further out to the side. It will get furthest away from the point of rotation. and the lighter objects will stay closer to the center. And that's called centrifugal force. It's how separators and purifiers work. So a typical application for this hydrocyclone might be oil and water. We'll have oil and water coming in here, and then the oil and water will be fed into the cyclone. There'll be a cyclonic action inside which will create a vortex. The oil will exit through the top because the density is less than water, and the water will drop down to the bottom. So the water is the reject. And if we want to see this in action, let's just push the play button here. We've got to slow that down as well, it's a little bit too much. You can see it comes in around. We can follow it all the way down. Down. The red goes out, and the blue, which here is the acceptance or the accept product, will go upwards. But there are a few design considerations here, and we're going to talk our way through them now. And one of the interesting things about the cyclone is its simplicity. There's only two main characteristics that define how the cyclone works. One is the flow rate into the cyclone, and the second one is the geometry of the cyclone itself. Now imagine for a moment that we had the gas stream coming back in here. The heavier particles wouldn't be able to change direction immediately, and that means they're going to strike the side of the cyclone here. Now the gas itself will continue to go around, and as it did so, the smaller pieces would also start to bang in the sides of the cyclone here, and they would drop down, so they'd be falling out of the gas stream. But what's interesting is, as the cyclone becomes narrower and narrower, it can actually remove smaller and smaller particles. And this is simply because the particles need to change direction very, very quickly. So it's the geometry itself which defines the filtering properties of the cyclone. And then for hydrocyclones, you can define the density of the two solutions that are separated. There are numerous applications of cyclone separators, and with good reason. They're cheap, they're simple to maintain, and they function relatively well. One example of where you would see a cyclone separator would be a sawmill. As wood is chopped, there's a lot of sawdust and dust in the air, and what you'll have is an extraction fan linking to a cyclone separator. The wood chippings will form the reject and drop out of the bottom port here, the bottom discharge, and then the accept, which is clean air, will go out the top. Perhaps one of the biggest advantages is that cyclone separators don't get easily clogged. Now imagine trying to filter out the sawdust from a sawmill. This would be very difficult, the filter would be blocked very quickly, whereas if we use a cyclone separator, we'll be able to take the sawdust out of the air and then discharge clean air and sawdust at the bottom without it becoming blocked very quickly. And this is essentially one of the big advantages of using a cyclone. You'll also see these cyclonic separators used for things such as oil and gas separation. Is particularly relevant for refineries. If any of you sitting at home have ever heard of Dyson, which is a vacuum manufacturer, you'll know that Dyson uses cyclonic separation, but there are no bags in a Dyson. And the reason is they use cyclonic separation. Dyson, the inventor, actually made himself a billionaire by applying this simple application for a household device. The materials used for cyclone separators vary, and there's a good reason for this. If on the suction side here you have a lot of coal and dust, etc., you may find that a material such as metal is not best suited for the task. The reason is there's a very high erosion rate, and if there is metal used for the cyclone separator, you may have an internal inlay here, or a coating, potentially ceramic or rubber or plastic, poly-based material. And poly-based materials don't erode as fast as some metals. The downside is that a lot of poly-based materials are a lot more expensive than metals, so you'll often have a metal cyclone separator with some form of coating on the inside. Another thing that you will need to take into account when selecting a cyclone separator is if the gas stream itself or the fluid stream is corrosive. If it's corrosive, then you may find that metals are not suitable. It might be better to pick a poly-based material. Anyway, it's a simple bit of kit, but I find it quite an interesting piece. It does pop up in many plants and many applications, so it's worth knowing a little bit about. What I'll do now, I'll just back out a little bit, and if you do go to the website, check out the introduction. It'll give you a bit more information. You can read the entire theory here of exactly how it works, etc. And you've also got the working principle and the animation. If you want to help us out, please do share the video and like the video, etc. If you really want to support us, then please go to our Patreon page. Thank you very much for your time.